we're going to grace him 5 extra, which will get us 10. All right. Finally, last but not least, Amir Caspi from the Southwest Research Institute on Citizen CATE 2024.
Cool. Thank you. Thanks for the invite. It's a pleasure to be here, and I'm happy to hear everything that everyone's doing. Thank you, Chris, for going ahead of me, and that way you introduced the concept of this dynamic distributed network, as well as all the other folks that have done similar stuff. So I'm going to rush through these, hopefully in a meaningful way, but obviously we're time limited. So as people have said, we needed to have a science question. The science question that drove us as solar folks is what's happening in the corona. Obviously, that's the best thing you can do with eclipses. But in particular, what you can see here, this is a movie that's made in extreme ultraviolet, and you can see it's made in a particular way where the instrument has been pointed away from the sun to actually look further away from the sun than it normally does. And what you can see is that there's a lot of really interesting dynamics happening here. There's a lot of interesting connectivity, changes in the solar corona, flows that are going through here. There's a lot of energy being processed in this region that we call the middle corona. Now, the problem is that most of the time you don't see it. Most of the time you have images that look like this from a space-based orbiter, and you have these other coronagraph images from other space-based instruments, and then you have this giant black ring where you have no observations. And you can't see what's happening in this region that is processing the energy and material that's flowing from inside the inner corona out to the solar surface. And so that covers a fairly significant gap of the solar corona. Now, you can try and get as close as you can with ground-based coronagraphs. This is the K-core from Hawaii, which until recently was covered in lava, but is now back operational. They actually helicoptered people in to recommission this thing for the eclipse. But of course, it's a ground-based coronagraph, which means that you're dealing with the bright sky, you're dealing with bird poop on the lens, you're dealing with whatever, right? And so there are limitations of ground-based coronagraphs, there are limitations of space-based coronagraphs, and it turns out that having a total solar eclipse gives you the best of both worlds. It gives you ground-quality instrumentation, but space-quality observing, and allows you to study things that you wouldn't be able to study in other ways. But the problem, of course, is that if you are a single person and the eclipse passes over you, you get a couple of minutes in totality, right? In this case, up to 4 minutes, 28 seconds for this particular eclipse. There's a lot of stuff happening in the corona that has timescales much longer than 4 minutes, timescales of tens of minutes, maybe hours. You can't chase the eclipse very easily, but you can make the eclipse chase you. And this is something pioneered by Matt Penn and Bob Baer and the folks at SIU when they ran Citizen CATE 2017 and distributed people all across the eclipse path with identical observing equipment to make it like one big instrument that happens to be tracking the eclipse. And we were fortunate enough to learn from them and take all of those lessons learned and improvements, and we did the same thing, the next generation of it for 2024. Where we had 35 teams of community participants distributed across the path. But we focused on a different science question. We focused on measuring the polarization of the corona. So you may know that light is a wave. The direction in which that light waves is called its polarization. And the light from the corona is actually polarized. And it's polarized because of the way that light is generated and gets to you. Now, you might not be familiar with polarization from a scientific sense, but you're familiar with it every day because you wear polarizing filters on your face all the time to cut out the glare that happens to be polarized in a particular way. And we did the same thing. We put little sunglasses on our cameras, not really, but the detectors have little polarizing filters in front of each pixel so that you can observe different polarization states simultaneously across everything. And then we followed a very similar pattern to what Chris just described. We took high dynamic range images by taking short exposures followed by long exposures, all in a sequence, back to back to back to back, and we put them together in this high dynamic range image that allows you to then observe the full range of the corona from the inner corona out to about 3 solar radii from the center. And you can see an example of one of the HDR images that we took in Australia in 2023. One I'm showing you here is going back and forth between two of the different polarization states measured by the detector. So basically, imagine if you took your glasses and you looked at them this way, and then you looked at something this way with your glasses this way. These are a prop, by the way. It's not just because I'm lazy. So I actually did this, by the way, during the solar eclipse in Dallas. I actually took my polarizers and did this. You could see it with your eyes, how the corona changed. But you can see here, the corona is changing as we go from one angle to another. And that's, again, because of the physics that's happening in the corona. It's much more striking, of course, if I overlay them together. You can see in blue and gold the two different angles. And the stuff that looks white is not white because it's super bright. It's white because it's not polarized. It's because that light is being generated in a different way than the light that is polarized. And when you measure the amount of polarization and the direction of polarization, that tells you something about the physics of the corona, which I could spend hours talking about if I knew what I was talking about, but I will leave that for somebody else to do. Now, those are just two angles. Of course, you can solve for every angle of polarization because we make enough measurements to do it, and that's what you get here. Now, this image was taken as a beta test in Australia for the 58-second eclipse that we got in April of 2023, but it allowed us to see everything. The colors you see there are mapped to angles. So magenta is red, and so on and so forth. Magenta is 0, not red. Of course it's red. Okay. Sorry, I need a minute back for that mistake right there. We have a paper online. You can read all about it. We distributed our hierarchy so that we didn't have to train 100 million people. We trained coordinators. Coordinators trained coordinators. They trained their local teams. We got into the business of opening a warehouse for stuff. We bought 35 sets of Pelican cases, cameras, detectors, because our teams couldn't be asked to afford this. This is $8,000 of equipment per station. And so we provided that to the teams. We packed it in, Tetrised it into these Pelican cases, delivered them down, and we held a training workshop with our regional coordinators in January in San Antonio. They then took that knowledge and passed it on to their teams so that we could have this distributed network and accomplish a lot more than we could by ourselves. And I just want to call out a special guests here sitting in the audience are members of our CATE team from Madison, from One City Schools here, who were thankfully... And thanks to the AAS for allowing them to come here and be part of this project and part of this presentation. So we are still doing surveys. They have to go through internal review boards because it's human subjects, but we're still doing surveys to figure out the impacts. But we had 379 applications for 35 participant teams. It was really hard to whittle those down. We had 225 plus participants over 43 different stations. 50% of our participants were women. And two teams had indigenous participants. We had a lot of Latino participation. We had 10 student lead trainers, and I'm sorry, I'm going to run a little bit long. 50% of teams with student participation and a U.S. Air Force Academy team. 100% success in getting people out to the eclipse. Not 100% success in observing it, unfortunately. There's a lot of photos here, so I'll just scroll through them very quickly, but you can see that people were excited. They were set up. Our Slack was blowing up on the day of the eclipse as people were looking to participate. Unfortunately, some people just saw the image in the top left, which are clouds. Thankfully, not many. We only had about, I think, 4 sites that were clouded out of 43 stations. A lot of people got eclipses. A lot of people were analyzing the data. Some people decided to jump ahead and analyze the data on their own, which is great. Some people got some very interesting structures in front of the sun. For those who are having trouble processing, that is a skydiver in front of the sun there. And that's an airplane on the other one. So we had 36 community participation teams. At least 85% of them were successful, partially or fully, in observing totality. We had 3 professional-led stations and 3 outreach stations for a total of 47,000 eclipse images that were uploaded. A terabyte of data. Yes, I know. Thank you. Including calibration, we had 86,000 images, over 2 terabytes of data. All of it was uploaded. We are receiving thumb drives in the mail now, and a bunch of local news stories. So as I am finishing up my time, I just want to wrap it up by showing you the processed pictures from a handful of sites. These have been manually co-aligned. We're still cleaning up the data. The site names are up at the top, and you can see these are processed in that same rainbow way that we process all of these. The angles are a little bit off between them because we're still co-aligning. But one of the cool things that we can do is, in addition to doing the angle of polarization, we can measure the polarization brightness, or how polarized was the light, and that tends to bring out a lot of different features. So here I'm showing you just 3 examples from early, this is North Texas, to I believe it's Illinois and Missouri, sorry, as my Missouri person sits there, and finally Maine. So you can follow along on our website. All of the data will be public to everybody. You can download it to 2 terabytes of data and process them as you wish. And thank you again to the Citizen CATE 2017 and Deb folks for pioneering this kind of experiment.
Well, we are a little over, so I think we'll, anyway, I'm sure you're all speechless from looking at these images, so you don't have any questions.